Okay, so that was basic about the cast metals. What we saw in the cast metal was we saw 4 types of the cast metals, right? We saw the similar 4 types in gold cast metals, type 1, 2, 3 and 4. We saw that type 3 and 4 of the gold cast metals could be age hardened. Then we saw what age hardening was and what annealing was. Remember that? Softening heat treatment and hardening heat treatment for the gold alloys. We also saw then the cast metal, what was the difference between high noble and the cast metal. Remember the percentage? What was the percentage of gold in high noble metals? Percentage of gold in high noble metals. Forgotten? It's okay to forget, but think. Sana, you remember a value, but yeah. It's 60% of all noble metals and 40% of gold. Okay, more than 40% of gold and more than 60% of total all noble metals, including your, isn't it? So that's okay. At least you remember one value. Now this time you will not forget it later, isn't it? Now do you remember the noble metal composition? How much was the percentage of noble metals in noble metal? I'm not noble metal alloys. Okay, was it, if I give 25% exact, 25% exact, will it come in noble or will it come in cast? If I give 20, okay, so it was 25, more than equal to 25% was noble. That means if it is 25%, it will come in noble. When it is less than that, it will be cast. Isn't it? It was more than equal to 25 was noble. So be careful about that 25 value because that will become a tricky part. Okay guys, so you all remember quite a bit of cast metals. Now let's move on to wrought base metal and gold. Okay, now you have that cast. Okay, imagine a scene. You have a big square mold. Okay, and to this big square mold you have actually put your cast metal and a chopon biscuit ke jaisa you have it in your hand, right? This is a cast metal. Now when you cold work upon this cast metal, you can make it a wrought metal. How? Actually, इस पे अगर बहुत stress डालो, if you actually take the cast metal and if you give it a shape, है ना? And if you keep giving it a shape for a certain duration of time, you will realize that now after a particular time you can no more alter its shape. It actually becomes harder. Okay, that's an important point in a cast metal property. This particular hardening of the metal because of some cold working on it is called as cold working, strain hardening or work hardening. That means if we plastically deform a casting, it becomes wrought. Okay, so amazing, right? Just changing the shape. See, Kamal, we take a cast gold metal. Matlab we have taken a first an alloy. We have taken a molten alloy and we have casted it. Casting procedure yaad hai? We have casted it. Now we got a small biscuit of that particular cast metal. Right? It has solidified. We have taken it out of the investment and we have that small biscuit of that cast metal. Now we deform it. उसको ऐसे bend करके उसको shape देंगे हमको. Okay? Yes, खींचा जाने के बाद you will notice that after a particular point of time you are no longer able to alter its shape. It has become very hard. Matlab its basic properties are changed. So this type of process of converting a cast metal, now whatever you get is a wrought. Okay? Now whatever plastic deformation, so you could give it any shape. You could give it a shape of wires. These wires could have, or anything. Yeah, malleability, Rashmi, yes, anything is a property that is present in the cast metal. Once you actually make it into the sheet, you will realize that these sheets themselves are very hard. Okay, that property is achieved by cold working. So ये जो हमने उस पे काम किया ना, the pressure and everything what we have put on this particular cast metal to get converted into something that is converted into wrought metal now. Once it is converted to wrought metal, its properties changes. It becomes more harder. It no more remains that ductile and malleable. एक बार शीट बनाने के बाद अब उसके वायर बनाने की कोशिश करोगे तो पता चलेगा they are not getting converted to wire because their actual properties have changed. Okay, getting the point? And why this properties change? Because you have put some pressure on it, you know. And it's not कि एक बार करने से या ऐसा कुछ, उसकी पूरी specifications है, how do you actually do it and all that. But basic thing what is happening here is your forces in the cold state itself are changing the property of the metal and converting it from cast to wrought. So cast metal से wrought metal, how do you make it? By plastically deforming it. So when a casting is plastically deformed, it is considered as wrought metal. Okay. So cold working, this conversion is also called as cold working because we are doing that at low temperature. Strain hardening or work hardening. See that? Now compare it with other terms. Remember the other terms, that is age hardening and annealing. Okay? ये दो टर्म हमने पहले देखे, age hardening. In age hardening and annealing, they both are heat treatment method. They are the heat treatment to alter the properties. But look at this one. Here we are not applying any heat. It's just the pressure and forces we are applying. Yes. So that's the difference between that. But this is also one of the way. So that is why it is called as cold working. Strain hardening because we are putting strain or we are working on it. So it is called as work hardening. Okay. So age hardening क्या था? It was a heat treatment, isn't it? Annealing क्या था? It was again a heat treatment of metal. So hope you are able to compare them and hope you don't get confused with these terminologies. Okay? This is very important to segregate all this in your brain. क्योंकि books में इनकी खिचड़ी बनी रहेगी तुमको. You will come across it every now and then and actually it gets confusing. What are they talking about? Right? Now effect of cold working can be reversed. Now look at this. Remember हमने age hardening को कैसे reverse किया था? We had actually reversed our age hardening with annealing. Similarly, cold working can be reversed by simply heating the metal and quenching it. That is annealing. So annealing can reverse the changes in the metal. Okay? Let me ask you one thing. Which is harder, wrought metal or a cast metal? What is harder? Hardness is more in wrought metal or cast metal? Yes. Kamal, after annealing actually we get a basic cast का जो basic property थी वो मिल जाती है, right? Now इसको if you are actually cold working again, you can get a wrought metal, or if you want to heat it and age harden it, you can go ahead and age harden it. Metal has the property of getting converted to one form to another. You can actually alter its properties by these heat treatments. So when we say hardening, उसको हम ऐसे नहीं बोलेंगे कि annealing का reversal है, because that annealing is actually bringing it back to its original cast properties. उसको we call it stage 0, you can say, isn't it? So that is why it is not said like that कि we are reversing the property of annealing. Reverse किसको बोलते हैं? When we go to a particular point and come back, but point 0 से वापस जाओगे तो उसको reversal नहीं बोलेंगे, right? So it's just the matter of terminology. Getting me? Yes, we can change the property. जो annealed metal की property को फिर से हम work करके we can make it again a wrought metal, definitely. But we don't call it reversal. Isn't it? समझ में आया ना, मतलब concept क्या है है, उसको रिवर्सल क्यों बोल रहे हैं हम? Why are we calling that process as reversal of properties? Because we, एक terminology है, some place we have to consider okay, this is a starting point, isn't it? So that cast metal is a starting point of us, and we can bring by annealing to back to the starting point, right? All clear till now? Which is more ductile, wrought metal or cast metal? Which is more ductile, wrought metal or cast metal? Yes, you guys got it very perfectly right. Now this was a question in Comet K 2010. अभी कौन सा चल रहा है? इसके पिछले साल वाला क्वेश्चन है. उसमें सिंपल क्वेश्चन पूछा था ये डक्टिलिटी और मेलिएबिलिटी ऑफ द कास्ट वर्सेस रॉट के बारे में. लेकिन इमेजिनेशन ऑफ द स्टूडेंट्स वाज कि when we use the wires, orthodontic wires, they are wrought metal, right? Isn't it wrought metal wire? Then वो wire है, मतलब वो ductile है. ऐसा नहीं है. You understand the scene now. We had converted that cast that was originally some block to the wire. So cast was ductile, उसको हमने wire तो बना दिया, but this wire is no more ductile. उसको ऐसे से करते तो टूट जाता है, it becomes brittle, isn't it? So wrought metal is more brittle than cast metal. Wrought metal is less ductile and less malleable than cast metal, right? Okay, now अभी हमने annealing, we just saw how we use annealing to reverse the property of two things. One is for cold working and second is age hardening. We reverse these two things by annealing. Now look at the process of reversal of annealing. It takes place in three stages. One is recovery, recrystallization and grain growth. We'll see it diagrammatically. Okay, now rule of thumb is when we actually are reversing or when we are actually annealing, we use approximately half the melting point of the pure metal or the fusion temperature of an alloy on an absolute or a Kelvin scale. Okay, now there are various scales of temperature measurement. You all must be knowing that we have Fahrenheit scale, we have Celsius scale and we have the Kelvin scale. Kelvin scale is the only absolute scale of the measurement of heat or the temperature. अभी बोलोगे absolute क्या होता है? This is the only one that has a zero. Zero के नीचे it doesn't have any temperatures. Okay? अभी if you want to go ahead with this more information, you can just Kelvin डालो Wikipedia में and पढ़ लो. It's a general knowledge which we actually saw in our 12th and all those things. I will not suggest you to go into much of that, but Kelvin is the only absolute scale of measuring the temperature. So Kelvin scale पे we want the melting point, the annealing temperature is half the melting point of the pure metal in the Kelvin scale. That is one fact which could be asked in MCQ. Now look at this. Normally cold working में क्या हो रहा है? Cold working में when we are actually cold working, right, the ductility comes down, isn't it? How it comes down when we start cold working, you will see, when you actually start making wires or sheets out of a cast metal, शुरू में when you put a pressure, the first pressure it has to be more, but slowly you will see it become more and more malleable easily. But after a particular point, suddenly the malleability comes down. Okay, that's what happens. Imagine you just take a block and start beating it to make the sheets. When you first पहला जब हथौड़ा मारोगे तो थोड़ा it will not be so easily flattened, but when you do subsequent ones it will be easily flattened, but after a particular point it will stop being flattened. Okay, so that's what happens here. Initially the ductility goes up, then the ductility goes down when we are cold working it. But when we go with heat softening, annealing, we get back the ductility, right? And the process is, first is here the recovery, then during the recrystallization we get back the ductility, and then there is the grain growth. The grains that we have achieved, they grow. So we achieve back ductility during recrystallization. So that's how the process of annealing works. Okay? Abhi, we use steel a lot. You all must agree to that. कि सारे orthodontic wires, everything we use in steel. Yeah, Sonia, I'll just go back to the last slide. Okay, shall I move on? Diagram बना रही हो सोनिया? You can just take a snapshot if you want. If you want to do that, एक command है, function print screen on your laptop. Okay, function print screen करो. कोई भी वर्ड या पेन डॉक्यूमेंट खोलो, उसमें पेस्ट कर दो, कंट्रोल V. फंक्शन प्लस प्रिंट स्क्रीन की बटन. In some computers you can actually directly use print screen, and control plus V. I mean, I'm just telling कि कभी कभी जैसे you wanna just take अच्छा picture है, you wanna just have it, right? You can just use this. Okay. Anyways, let's move on to carbon steel. Well, drawing and writing is the best habit if you are, if you are taking down the notes and scribbling that, because it will help you remember also, definitely. Okay. Now, when we use steel, when we talk about steel, these steels, carbon steels, are iron-based alloys that contain less than 2.1% carbon. Okay. When we talk about iron and carbide alloys, iron and carbon, these iron carbide alloys usually have more percent of carbon, 4%, right? Up to 4%. Then when they have more percent of carbon, they are cast irons. Okay, that is what is iron carbide. There are burrs, cast metal burrs, cast iron burrs, right? These burrs, they have a very high cutting efficiency. Okay, they are harder, but they are brittle. Okay, they are superior at higher speed used for cutting enamel. Since they are harder, okay, they can cut enamel, but something that becomes harder is usually less ductile. And anything that is less ductile is brittle. Brittle, समझते हो? Brittle, you get it? What is brittle? It's not elastic. If it bends, this thing. Is it 1.2%? You want break? Come on. No, it breaks, right? Okay, I'm so sorry. Actually, I was talking about this and this. Okay, is it 1.2% in notes? I'll just, yeah, come on, got it. I'll just check it, Sonia, which one is right. Now it's a value, right? 1.2, 2.1. It's from Philips. I'll just check it and get back to you. We'll do one thing. Anyways, it's 1 hour. Let's break for 5 minutes. Meanwhile, I'll check this one so that you people can immediately correct it if it's wrong there, or I will correct it if it is wrong here. Okay? Let's break for 2-3 minutes over here, and then we'll restart again. Okay? So we are talking about the carbon steels, right? So they have a high cutting efficiency, they are more brittle, and they are very good at high speed for cutting the enamel. Okay. Now steel has various shapes based on its structure. Basically, it has a lot of structure. So based on that, it can be classified as ferrite, austenite, and martensite. Now we'll just look at the difference between these three things. So when we say ferrite, ferrite is a body-centered cubic structure. So it's a cube and your carbon actually sits in the center. Right? So the basic structure of your iron is a cubicle, and in the center you have the carbon element sitting there. So that is what is ferrite. In austenite, it is face-centered cubic. Okay, so herein, rather than being at the center, they sit between the faces. So that's how it differs. And austenite, it can accommodate more of the carbon as compared to ferrite. Obviously, because it is putting that carbon in the faces. So it can accommodate more of the carbon as compared to ferrite. So in austenite stage, a steel or an iron can accommodate more carbon. Okay, and there is a property when this austenite, this particular phase is actually found between the temperature 912 to 1394 degree, and when it is cooled very slowly, it forms iron carbide, and that gives it the strength. So at a particular temperature, this austenite is achieved, and then it is cooled slowly to form iron carbide, that gives it a strength. Okay, now we already saw normally your iron is in ferrite stage. Okay, normally your iron is in ferrite state. It can accommodate less of the carbon as compared to austenite. Okay, when a plain carbon steel that contains 0.8% carbon, it is cooled slowly. Okay, first it is heated to convert into austenitic phase, then it is cooled slowly. When it is cooled slowly, do you remember we had been talking about that eutectic conversions, how it takes place during cooling at a particular composition, right? There is the solid state eutectic transformation that happens at this particular temperature, and you get two structure that is called as perlite. Now, which consists of an alternating lamellae of ferrite and cementite. Okay, let me explain this. This is actually a process of how we get that hard carbon steel instruments के लिए we get that particular edges, right? Hard edges. How do we get that? We actually have carbon steel that contains 0.8% carbon. Now this is converted to austenite, and then this is heated slowly. When it is cooled slowly, when it is cooled, there is a eutectic transformation that takes place, and that gives rise to something that is called as perlite. Now this perlite consists of alternate lamellae of ferrite and iron carbide. So you remember austenite existed only at a particular temperature. When we actually cooled it down, we are expecting it to come back to its ferrite form, but there is a eutectic transformation that takes place. Okay, it's a composition that contains a particular amount of carbon, that is 0.8% carbon. When it cools down, rather than forming a total ferrite, it forms perlite. This perlite contains alternate lamellae of ferrite and iron carbide, that is called as cementite. So perlite contains iron carbide and cementite alternating. Okay, this cementite is called as carbide. Remember carbide burrs? Why they have those hard edges is because of this cementite. Okay, this particular phase has an orthorhombic crystal structure and it is much harder and more rigid than both austenite as well as ferrite. This is how we achieve a very hard edge in carbide instrument. This is by the formation of pearlite that contains ferrite and cementite. The hardness is given by cementite. Okay, then we have something called as martensite stage. It is formed when austenite is rather than being cooled slowly. Remember when we were cooling austenite slowly, what we were getting is pearlite. But imagine if we don't cool it slowly and we just quench it in a water, what we will get is a body-centered tetragonal structure, that is martensite. So normally we do not use this pearlite method, we actually have the edges as martensite. Okay, because the edges will fracture if we have them too hard and brittle. They do fracture. Still the carbide edges are quite brittle and hard, you know, they do fracture, but we still have them as martensite. It decomposes to form ferrite and carbide. Remember in the previous this thing, we were actually cooling austenite and getting ferrite and carbide directly. Herein what we are doing is, we are quenching austenite and getting martensite, and this martensite then decomposes to ferrite and carbide. So ultimately we are getting ferrite and carbide, right? But this process can be accelerated by tempering. Okay, now this particular thing will reduce its hardness but increase its toughness. Total fracture resistance is increased and the hardness is decreased. A little confusing though, but hopefully you have a few of information, you know, gathered out of this particular two slides. That we have three phases, the ferrite, the austenite and the martensite. Austenite phase exists at a particular temperature, but when we cool it, we get martensite phase, right? When we cool it slowly, we get ferrite and carbide alternating lamellae, that is called as pearlite, but when we quench it suddenly, we get martensite. This martensite is the one that forms the cutting edges of the carbon steel, but it can get decomposed into carbide and ferrite, and this process is called as tempering. Got it or not? No? Confused? Okay, anyways, let's go on to ferritic and austenitic martensitic phases of stainless steel, then we'll talk about it more. You know, these are basically the phases and every phase gives it a little different properties. Now for you to understand, you know, don't go into the detail of crystalline structure of the particular phases. That is just, it doesn't matter if you don't remember, you know, how the cube would be and how that particular structure gives it a property. All you have to remember is what particular phase exists at a higher temperature, what particular phase exists at a lower temperature, what phase forms the edges of the carbon steel instrument. These are some of the facts which are typically picked up as the MCQ. Now if we talk about the carbide instrument, the edges are formed by martensite. That's what you have to know about it. You can know one thing, that martensite exists at a lower temperature. Comparatively, austenite existed at a higher temperature. Remember that. These are some of the things you need to understand because we have applicability of these things. Okay, when we see the applicability, you will be able to know why we are talking about austenite and martensite. right? So let's move on to making the steel stainless steel. Now you all know that what is carbon steel, what is iron carbide, right? What is the one that has, how the one iron, why we have carbon in iron. Now let's make that particular iron as stainless. We add chromium to it. Okay, when we add 12 to 30% of chromium, it becomes stainless because of the passivating effect of chromium we already saw, right? But the problem is cutting efficiency is low and it becomes dull very rapidly. So as compared to the carbide, cutting efficiency of stainless steel is less and they are superior at low speed and used to cut dentine. So see the facts. We have carbide instruments that are used to cut enamel because carbide instruments are harder than stainless steel, right? But the edges of the carbide instruments, they are brittle, right? But compared to stainless steel is not brittle. It will, but it will become dull and it is not so hard. We use at low speed stainless steel, at high speed carbide, right? For dentine stainless steel, for enamel carbide. These are the MCQ facts over there. Right? Now the chromium composition has to be between 13 to, now look at this, now I contradict, it's 12 to 30 or 13 to 28, it is nearly the same value. Okay, so you can just choose anything. This is more precise and this is a little bit more bigger range. So if the chromium content is less than 13%, it will not be effective. But if we increase it more than 28% or 30%, it will make the steel brittle. Okay, so that is why we want this particular range. So below that range it is not effective, but above that particular range it will make it brittle. Now let's talk about these three phases which we already discussed in stainless steel. Okay, now clear your mind with the things, relax and look at this. Okay, ferritic are the one that is used in the manufacturing of the instrument. Okay, it gives us some degree of tarnish and resistance, and chromium is 15 to 25. Okay, chromium steel instruments. So we use them, but they have some degree of tarnish resistance. Now look at the martensite. Okay, they have lower chromium content. This steel is hardened. So martensite are comparatively hardened by heat treatment. They do not have very high tarnish resistance. Resistance is moderate. Because anyways they are stainless steel, so they need to have some resistance, but this resistance is moderate because composition. 12 to 18. Now go back and look at that one. It was 15 to 25. Remember the values. Okay. Now austenitic. It is the most extensively used for dental appliances. I think so this part is there in your keynotes. Okay. It has a form of chart or something, I think. Do you want me to go back again? Is it done? Okay, I'll refresh my slides in a second. That will just improve the speed a little bit. Okay, voice audible? Are you able to hear me? Or are you feeling the break in voice or something? Now is it okay? Because actually I felt that my speed dipped a little, but I refreshed. Now is it okay? Come on. Okay. Yeah. Whenever you have a voice lag suddenly or something, because it may happen in the mid or after the class, so you can tell me so that I can just, refresh from my end, and that would do the thing. Okay. So we have been talking about austenitic, which is used very extensively for dental appliances, and the most common one is 18-8 stainless steel because it contains 18% chromium and 8% nickel. It has the greatest resistance to tarnish, corrosion, and carbon content is less, that is 0.08 to 0.2%. Okay, now we already saw that martensite is used for surgical and cutting instrument, while austenite is, there are two varieties. It's 18-8 stainless steel. There are two types. Type 302 that has a little bit more of carbon, and type 304 it has a little bit more of less of carbon. But what point is that makes it this thing 18-8 is nickel chromium, 18% chromium and 8% nickel. This is important, and this is MCQ. Okay, they are more ductile and all that. How much carbon in? Come on. We saw, right? It's 2.1. Austenite, here we have this thing, see, two things. One is 0.15, that is type 302, and type 304 is one more variety which has less of the carbon, 0.08. Okay, we saw that steel has a good corrosion resistance because of its chromium, but we can make the steel lose its corrosion resistance when it is heated at 400 to 900 degrees centigrade. If you ever have, agar steel ko you put in a big hot furnace, it becomes all cracked, it loses its layer on the top, and it actually loses its stainlessness. Okay, so that happens because of precipitation of chromium carbide. This could be prevented by adding titanium. Okay, if we add titanium, so even at high temperature, it will precipitate the carbide in preference. So chromium will be not lost. So when we heat it at a very high temperature, actually chromium is lost because it combines with carbide. If we add titanium to it, this is there, na? It's a snapshot of your keynotes, Sonia. This one, it's the same information in the chart that has been elaborated. That's it. I mean, ultimately the gist is that chart, what you need to remember. This is for your explanation. Anyways, if you want to take a snapshot, it's here. Okay? Okay, now when we talk about the various composition, then see, look at this, we have various alloys and the corrosion resistance over there. So this is just for the information. I would, this is, you know, something which you have to remember. You get MCQs directly on that. What is alloy? Alloy is cobalt, chromium and nickel alloy. What is beta titanium? It is titanium, molybdenum and aluminium alloys. We are talking about these alloys, right? So this composition is important for some of them. Then we have nitinol. Nitinol is again one of the very important one. That is a nickel titanium. Okay. Now nickel titanium, it has two important properties. That is shape memory and pseudo elasticity. Super elasticity or a pseudo elasticity. Super elasticity and shape memory, these two properties are present because of the same austenite to martensite transformation. We just have a look how these two properties are present. Okay, now let me go down here. We already saw that martensite exists at lower temperature and austenite exists at higher temperature, isn't it? Now, both the properties are because of the conversion of martensite to austenite. Now look at this. Now we'll talk about one property, the shape memory thing. Okay, so we have the wire in austenite form. We cool it. We cool it by either keeping in the refrigerator or, you know, we make it cool. We convert it into martensite phase. Okay, and then we bend it. Okay, now when this bent thing is inserted into the oral cavity and it is heated because of the temperature of the oral cavity, it will try to get back to its shape. That is what is shape memory effect of nitinol. Getting the point? Are you able to hear me? Yeah. See, what we have a wire. This wire is in austenite form. Now when we actually cool this wire, it gets converted into M form or martensite form. In the cool stage, we deform the wire. Okay, and we make certain appliance or whatever. Okay, now we put back in the oral cavity. In oral cavity, it will get heated because of the oral temperature. So it will come back to its original shape because now martensite is getting converted to austenite again. Okay, so because of this austenite to martensite and then martensite to back, it has its shape memory effect. Getting the point? Okay, but that is changing the temperature. The second effect, that is super elasticity, it is done by applying stress, right? Now you all very well know that stress also results in changes in the property. So we have austenite wire, okay? We apply stress. It gets converted to martensite. We release stress. It will get converted back to austenite and it will become straight again. So that's the super elasticity, and you know, normally elasticity is present in most of the steel and other things, but nitinol has 10 to 30 times more elasticity than a normal springy material. It's very elastic. Okay, because of its martensite to austenite conversion. Clear?